Hey guys, we will solve this problem today. So we have a freezer compartment which is cubical and it's 2 meters on a side, and we have given we want to insulate that cubical cavity. So we have a styrofoam of thermal conductivity 0.030 watts per meter Kelvin, and we want to ensure heat load of less than 500 watt, and we are given inside and outside temperatures. So let us first write down what are the known factors here. So temperature inside, temperature outside, we know the dimensions of the cube, we know thermal conductivity for the styrofoam, and we know the limiting value for heat loss. Now what we want to find is thickness of styrofoam, which should be enabled to keep the heat load of less than 500 watt. So now in this problem we will first draw our schematic. So we have a cubical cavity and it is perfectly insulated on the bottom, and we have to give it a styrofoam thickness to prevent heat loss. So let us draw this thickness. So this is our styrofoam, and the inside dimensions are 2 meters, not the outside. So this is our styrofoam. The inside temperature is minus 10 degrees Celsius, which is T inside is minus 10 degrees Celsius, which is 273 minus 10 is 263 Kelvin. T outside is 35 degrees Celsius, which will be 273 plus 35, which would be 308 Kelvin. So uh, we we know the temperatures, we know the dimensions, we know the limiting value for heat loss. It should be less than 500 watts. So let us, like, what are the assumptions here? So first would be perfect insulation on bottom. There is no heat loss through the bottom. Second is there is a steady state heat transfer. And third is our K value, the thermal conductivity value is constant throughout the temperatures. And fourth one, this assumption is very important in this case, is one-dimensional heat conduction. The heat conduction is happening in only one dimensional. So let us calculate this problem. So we have a cube, so we know all of its sides are the same. So cross-sectional area will be same for all the sides. So let us take it for the one side first. So we know by Fourier's law, Q heat loss is equal to minus thermal conductivity multiplied by cross-sectional area delta T, which is difference in temperature divided by thickness of the conduction medium. So we will simply put this value 0 K is 0.03, area is 2 multiplied by 2 as it's a square. Delta T would be 308 minus 263 divided by thickness would be T. So this is the value of heat transfer from only one wall. Now, since the bottom surface is perfectly insulated and we are given a cube, so we know cube has six sides, but one of them is perfectly insulated. So we are left with five total sides for this cube. So the same amount of heat transfer would be happening through all five walls. So we will multiply this equation by 5 and we know the limiting value for the heat loss is 500 watt. So if we take the worst case scenario, they are saying we should limit the value of heat loss to 500. So if we take the worst case scenario as 500 and then calculate the thickness for this value, all the other values greater than So all the other thickness values greater than this calculated value would be sufficient for us. So let us calculate T from this. So if we solve this, we get 0.054 meters or 5.4 centimeters. So if we go here, so this is the thickness value for this styrofoam would be 5.4 centimeters on each side. Now this value is only possible because we are assuming it's a 1D heat conduction. So we are not considering these corners because the heat is going in only one dimensional, one direction. So and like if we consider this in our real world, so basically this is a design of a fridge. So if we have a fridge, we know its dimensions, inner dimensions, and we want to contain the heat loss from that fridge. So we need to use the styrofoam. So if we use a styrofoam in such a way which has a very less thermal conductivity value, so we can reduce the thickness of that styrofoam and reduce our costs as well. So this is one like real life scenario which where we can use this equation. So it is a helpful way to understand this problem in our real world. So thank you so much guys for watching. Please like, share and subscribe. Thank you. Bye bye.